Hi everyone, this is lesson 5.2, adding and subtracting rational expressions. And actually we'll start with reviewing or learning about LCMs and LCDs first. So LCM stands for least common multiple and LCD stands for least common denominator. So before we dive into what's actually on the screen right now on the video notebook that we're looking at, I think it will be good to do a quick review of what is LCM and what is LCD just with regular numbers before we get into the algebra problems, the algebraic expressions and the factoring polynomials and all of that. So I am going to switch the screen just to a blank whiteboard right now, and we'll kind of take some side notes first, just to kind of refresh our memories on how to find least common multiples just of regular old numbers and how to find least common denominators, again, just with regular numbers. That's going to be a good foundation that we'll need to make sense of what's about to come. Okay, and also just a reminder, you should have also watched the lesson 5.1 video before this. Those topics included some review of rational expressions, simplifying, multiplying, and dividing. Those topics were review or should have been review from intermediate algebra. What we're about to do, you may have seen before, but it would not have been at Metro. So I'm glad you're watching this video and let's go. All right, so I'm switching my screen, like I said. Let's just do some basic review of how to find the least common multiple just with regular numbers. So I'm going to do an example with the numbers 12 and 30. Now, oftentimes if I do this example in class, students will shout out an answer or think of an answer such as 2 or 6 or 3. And when you're thinking of those numbers, what you're thinking of are factors or greatest common factors that go into 12 and 30, and that is not what we're going to find. We are finding multiples of 12 and 30. So whatever this answer is, it has to be either equal to one of these numbers or bigger. So it's not about what goes into 12 and 30, but it's about what they go into. And some of you could probably kind of stare at these two numbers and you already know the answer because you're just good like that and you can do things in your head. I'm going to take us through a little more detailed process because we're going to need that when we go back to the algebraic expressions. So we're going to factor each of these numbers. I'm going to do it using a factor tree, but we're going to get into actual factoring polynomials later. So let's start by factoring the number 12. So I just kind of start branching off and I'm thinking of what multiplies to 12. There's many options. I'm going to start with 2 times 6. And I'm going to circle the 2, which is a prime number. I can't break it down anymore. Remember, a prime just means it's a number that is only a multiple of 1 in itself. So 2 is only a multiple of 1 and 2. 6, I can factor more. I can break that down into 2 times 3. So I've just factored 12 into 2 times 2 times 3. That's called prime factorization. Now let's do something similar with the number 30. We'll do it down below. So I'm going to break down the number 30, again, using a factor tree. There's many ways to start it. I could start it with 2 times 15 or 3 times 10 or 5 times 6. Any one of those combinations would be fine. We should end up with the same prime factors at the end, no matter how we start it. So I'm going to start with 5 times 6. 5 is prime. Then we'll break down the 6 into 2 times 3. So if you did it in a different way, the prime factors that you should end up with are 5, 2, and 3. I'm going to write them in order though. So I'm going to write, when I factor the number 30, I'm going to write 2 times 3 times 5. Notice how I'm going to start to line up the factors when I write them. So I've just written the factors of 12 sort of horizontally in a row here. I'm going to start lining up common factors of 30 right underneath. So let's see, 2 times 3 times 5. Okay, now the goal of this was to find a least common multiple of 12 and 30. So a multiple of 12 and 30 needs to have all of these factors in it. The least common multiple, we need to sort of do that in the most efficient way possible. We don't need any extra repeats. Okay, so what I'm going to do is I'm going to sort of treat this like each factor gets its own column. So I'm going to start with this 2 with the 12 here. The LCM definitely has a factor of 2. It's like I'm bringing down the 2 here. Now I'm moving to this next column. See how both 30 and 12 both have a factor of 2? They share that common factor. The least common multiple really only needs one of those. Okay, we'll do the same thing with the 3s. 12 and 30 each only have one factor of 3, and then the 5. Okay, if visually you can follow what we just did, that's great. If you're lost, that's okay. Here's another way to think about this. Maybe go back to the factor trees. 2 times 2 times 3, and then 5 times 2 times 3. See how in the factor trees, they both have that 2 times 3. We need that in our least common multiple. We need the 2, we need the 3. And I've just sort of circled them in red here. Now look at the other prime numbers in the factor trees that we haven't yet circled, or I guess circled again, boxed off again in another color. We're going to need those as well in our least common multiple. So another way to think about it is the number 12 has 2 factors of 2. We need both of those in our answer. Now 30 only had one factor of 2. So 12 had 2 factors of 2. 30 had 1 factor of 2. Whichever one has the most, that's how many we need in the LCM, the least common multiple. Let me circle that other number 2. So I just drew a little blue box around the 2. That was a factor of 12, and that 2 is also part of the least common multiple. And then we'll do the same thing with the 5. And there we go. Okay, now we haven't fully answered the question. We do need to multiply those together. 2 times 2 times 3 times 5. So 2 times 2 is 4, times 3 is 12, times 5 is 60. Okay, is there a shorter way to do this? Definitely there is with numbers, but we're not just dealing with numbers like 12 and 30. We're going to be dealing with trinomials and other things. So I did want to just get us warmed up by factoring each expression first, and then putting those factors together to form the least common multiple. Notice that we didn't use all of them, okay? So we didn't do 2 times 2 times 3 times 2 times 3 times 5. That would be bigger than we needed, okay? That would be a multiple of 12 and 30, but it would not have been the least common multiple. Okay, if that helped, great. If you feel more lost, then I'm sorry, let's keep going. And as always, hopefully it'll become clearer with more examples and more practice. All right. So here's where this fits in with the algebraic expressions. So we're back at the beginning of the 5.2 notes. So we're going to find LCMs by factoring. So here's what the first little paragraph says. To find the LCM, least common multiple, of 2 or more algebraic expressions, we find their prime factorizations. Okay, in other words, we factor. Then we use each factor the greatest number of times that it occurs in any one prime factorization. That's what I was attempting to show with the 2s and the 3s before. Let's see if we can make sense of this example. So our first example says, find the LCM of m squared plus 4m plus 3 and 2m squared plus 4m minus 6. So our first job is to factor each one of those. That's the prime factorization. It's just, see our previous unit on factoring for how to do that. So m squared plus 4m plus 3 gets factored into m plus 1, m plus 3. So our LCM definitely needs both of those factors. Then the other expression, 2m squared plus 4m minus 6. Okay, there's a GCF of 2. Notice how we're taking out a 2 first. And then we're left with m squared plus 2m minus 3. Each of those terms got divided by 2. The m squared plus 2m minus 3 gets factored more into m minus 1, m plus 3. So let's take a look at all our factors. We have m plus 1, m plus 3, 2, m minus 1, m plus 3. So the LCM is going to have all of those factors. However, we're only going to use each factor the greatest number of times it occurs in any one factorization. So notice how we have one factor of m plus 1. We have one factor of m plus 3 in this first expression. So we need at least one of each in the LCM. Moving on to the next expression, we have one factor of 2, one factor of m minus 1, and then take a look. We also have one factor of m plus 3. But see how it's like we already had one. We already had one from the other expression. It doesn't ever occur twice in a row, so we don't need it twice in a row in our LCM. We only still need it one time exactly in our least common multiple. Here's one approach I might take in writing this out. So what I often do is I just start with the first expression and just write out both of those factors, m plus 1, m plus 3. I know I'm going to need both of those. Then I take a look at the second expression and I take a look and see, is there anything missing? Okay, this 2, that's new. I'll add that. Just stick it in the front there. This m minus 1, that's also new. I need that as well. So I'm writing it kind of at the end here. The m plus 3 is already there. So we already have it. So we don't need it again. So our full LCM has these 4 factors: 2, m plus 1, m plus 3, m minus 1. The order can be rearranged in any way as long as all of those factors are there. Working on this is getting us ready to find LCDs, which stands for least common denominators. So that's where we're headed with this. Okay, let's do some more examples. And as always, I've edited this video notebook document. So notice we're starting with example 3. Apparently when I made this, 1 and 2 were too easy. We skipped over them. All right, so example 3 is what we're looking at next. Find the LCM of x squared plus 5x plus 6 and x plus 3 squared. So our first job is to factor each one of those. So let's start with the x squared plus 5x plus 6. So we're going to set up our parentheses, fill in x times x. The last 2 terms multiply to 6 and need to add up to 5. So that's going to be positive 2 and positive 3. So we can fill in x plus 2, x plus 3. So our LCM is going to need x plus 2 and x plus 3. We know that for sure. Let's move on to the second expression, the x plus 3 squared. Okay, x plus 3 squared, you can just write that factor twice. That's all that is. So x plus 3 squared means x plus 3, x plus 3. So notice that there's 2 factors of x plus 3 in that second expression. But there was only 1 in the first expression. Okay, so the LCM needs however many of those is the greater number. So do we need 1 or do we need 2? Those are the choices. We don't need all 3, just however many, whichever expression has the most, that's how many we need in our LCM. So since the second expression has 2 factors of x plus 3, we need 2 factors of x plus 3 in our LCM, our least common multiple. The other factor that we need is this x plus 2. That's what we're filling in. So our LCM would be x plus 2, x plus 3, x plus 3, or we could write it as x plus 2 times x plus 3 squared. All right, let's see. Feel free to fast forward through this, but I'll try to do most of the your turns today, just for a little extra detail. So for the your turn 3, let's find the LCM of 2x squared minus 9x minus 5 and x squared minus 25. Okay, this first trinomial is a little bit harder. I can't factor out that 2, so I guess I'm just going to leave it there. Setting up parentheses, this is essentially using trial and error. 2x squared is our first term, so we can do 2x and 1x for our first terms in our binomial factors. Our last 2 terms need to multiply to -5, so it's going to be something with 5 and 1. And I think if I put the 5 last, I can sort of see the 2x and 5 will multiply to 10. Then I could put the 1 in the middle. That would be 1, 10x and 1x. Yeah, if I make the 10x negative and then the 1x positive, that'll do it. Okay, so let's just do a quick little check here. I was sort of saying it out loud, but here's the check. We're using trial and error. Our outside terms, 2x times minus 5 would be minus 10x. Our inside terms would be plus 1x. And we're checking that those add up to that middle term of minus 9x, and they do. Okay, so I factored that. That took a little more work. Now let's factor x squared minus 25. That's a difference of squares, x plus 5, x minus 5. Okay, now if all 4 of these factors were different, then we would just write them all together for the least common multiple. We would just need all of them. However, there is one that's shared, that's the same. So notice how both expressions have this factor of x minus 5. But each expression only has one of those, one factor of x minus 5. So we need one factor of x minus 5 in our LCM, our least common multiple. And then the other factors that we need are the x plus 5 and 2x plus 1. Okay, so there's our answer. X minus 5, x plus 5, 2x plus 1. All right, let's move on to example 4. Let's see, we're finding the LCM of x plus 2 and 2x plus 6. Write the prime factorizations. Okay, x plus 2 is just x plus 2. There's no way to factor that. That's why it says this expression is prime. So it's just a factor in itself, that's all. 2x plus 6, we can factor out a 2, and we're getting 2 times x plus 3. So for the LCM, we're looking at all these factors. There's nothing that's shared, so we just need all of them. There's nothing that's repeated that we need to pay close attention to. We just need one of each. Now I'm near the bottom of my screen right now, so I'm going to just jot this down, and then I'll scroll down to give a little more space. So the LCM should be 2, x plus 2, x plus 3. Possibly with a different order would be fine. Okay, I'm about to scroll down so that we can catch up with what else is here. There we go. Okay, let me clear my writing there. All right, so once again, we had 2 times x plus 3. So the LCM is 2, x plus 2, x plus 3. Yeah, it says these expressions do not share a common factor other than 1, so the LCM is their product. In other words, you just need all the factors together. So for your turn, find the LCM of t squared plus t and t minus 1. T minus 1 is prime, nothing we can do there. T squared plus t, we can just factor out a t and we'll get t times t plus 1. Yeah, so the LCM, we just need all of those factors together. T, t plus 1, and t minus 1. So that's like if I asked you what's the LCM of, I don't know, 6 and 11. 11 is prime. 6 is just 2 times 3. There's nothing in common there, so we just multiply all that stuff together. 2 times 3 times 11, which would be 66. It would have been quicker to just do 6 times 11, 66. Anyway, that happens sometimes. The two numbers don't share any factors. We just need to take all the factors of each and just put them all together for the least common multiple. All right, I think we made it through the first page. Now we'll do a slightly longer one. Example 5, find the LCM of 3 expressions. Okay, so we're kind of branching off of what we were just doing. Still the same concept, just we're going to have 3 expressions rather than just 2. So example 5, find the LCM of c squared minus 25, c to the third plus 5c squared, and c squared minus 6c plus 5. So we're going to factor each one separately, and then we'll go from there. So let's start with c squared minus 25. That's a difference of squares, c plus 5, c minus 5. Then let's move to the second one. C to the third plus 5c squared. There's a GCF of c squared. Now they're writing c times c. I would have just written c squared on the outside. And then inside we're left with c plus 5. But either way, same thing. And then finally, that last expression, the trinomial c squared minus 6c plus 5. Let's see, we have two parentheses, c times c. The last two numbers need to multiply to 5, so that'll be something with 5 and 1. They need to add up to -6, so they would both be negative. So -1 and -5. In other words, c minus 1, c minus 5. Okay, so let's look carefully at all the factors we have right here. Okay, so we definitely need this, it's right there. We definitely need this c squared in our LCM, so that's going on the outside. We generally write, if it's just a single variable, we'll write that first. Then let's start with what's up at the top in red here. So the c plus 5, c minus 5. We're going to need both of those, so I'm going to write them both down. C plus 5, c minus 5. Now, moving on to that second expression where we had the c squared, c plus 5, we already have the c plus 5 right here. We already wrote it down. And we know that we really only need one. It never appears more than once in one single expression, so it's already taken care of. Moving on to that third expression, c minus 1, c minus 5, we already have a c minus 5. So the only other factor left that we need is the c minus 1. So our full answer for the LCM is c squared, c plus 5, c minus 5, c minus 1. All right, let's do the your turn. Your turn number 5. Find the LCM of y to the 6 minus y squared, 2y plus 2, and y squared plus 2y plus 1. Okay, let's start with the first one, y to the 6 minus y squared. We can factor out a y squared there, and we'll be left with y to the 4th minus 1. Oh, that's kind of a tricky one. Interesting. That is a difference of squares in itself, so we can break that down more. This is harder than the one we just did, unless I'm reading it wrong. Well, let's keep going. Y to the 4th minus 1, that's a difference of squares. So let's keep factoring. That turns into y squared plus 1, y squared minus 1. Oh boy, and then the y squared minus 1 gets broken down more for the same reason. That's a difference of squares, so this becomes y squared plus 1. And then the y squared minus 1 gets broken down into y plus 1, y minus 1. Wow. Okay, so just to kind of recap just that tiny little expression that looks so easy, we took out a GCF of y squared, so we were able to subtract the exponents when we factored that out. And then we had a series of difference of squares that we were left to break down. So y to the 4th minus 1 broke down into y squared plus 1, y squared minus 1. We're able to do this because the exponent is even. There's a minus sign and there's a perfect square number, which is 1. Same thing with the y squared minus 1. That got broken down in a similar way into y plus 1, y minus 1. That's all from the first expression. All right. I'm worried I'm going to run out of space. So I'm going to take this second expression up at the top of my page. 2y plus 2. I can factor out 2, and then we're left with just y plus 1. That's all. And then finally, the third expression, the trinomial y squared plus 2y plus 1. That's a trinomial. You can break it down using parentheses, y times y. We need factors of 1 that add to 2. That would be y plus 1, y plus 1. All right. Now for the challenge of putting it all together. So we need all those factors. We just might not need repeats. So we'll try to be careful. I'm going to start with this one at the top that has the 2 on the outside. I'll just start with the 2. Write that first. Do any of the other expressions have anything just kind of on the outside? And I'm going to say yes, this one right here, this y squared from that first expression. Let's put it on the outside as well. So we're starting with 2y squared. Okay, what else? Let's see, let's go back. We'll work on the red one now. Y squared plus 1. And then y plus 1, y minus 1. We'll just copy all of that down. Okay, y squared plus 1, y plus 1, y minus 1. Now, moving to this second expression, the 2y plus 1, we already have the 2, we took care of that. What about this y plus 1? Did we already write down a factor of y plus 1? Yes, we did. So it's actually already taken care of. Now, finishing up with this third expression, the trinomial that we factored into y plus 1. Notice how there's 2 factors of y plus 1. So we're going to need 2 factors of y plus 1 in our LCM. We only have 1 right now. So that one's taken care of, but we do need that second one. So we can write it a second time, or I could just squeeze in a little exponent and just write squared on the y plus 1. It's up to you, whichever way makes more sense to you. I think I am going to write it a second time. I do like seeing the factors separated out. So I have 2y squared plus 1, y plus 1, y minus 1, y plus 1. Feel free to rearrange those in a different order. That's fine. All right, so that was a lot of work already, and those problems are already challenging. If I remember correctly, though, on your homework, I think it just starts with adding and subtracting problems. So all of this was sort of leading up to getting us ready to add and subtract rational expressions where they don't necessarily have a common denominator. Now, if you took intermediate algebra part 2 or the accelerated intermediate algebra before this class, you would have seen some examples of adding rational expressions when there was a common denominator. And that's as far as we got. We're going to see examples where there is not a common denominator. And of course, that gets more challenging. So up at the top here, or I guess in the middle of your page, but the top of my screen where it says adding and subtracting rational expressions, to add or subtract when denominators are the same, add or subtract the numerators, and keep the same denominator. So a over c plus b over c is equal to a plus b over c. Or 1 over 5 plus 2 over 5 equals 1 plus 2 over 5, which is 3 over 5. Add the numerators, keep the common denominator. And I could put an x next to the 5, and it's still true. 1 over 5x plus 2 over 5x is 3 over 5x. And then we'll complicate it from there. We'll get there. But that's kind of where we start. But what if these expressions did not have a common denominator? What if one of them was 5x and the other one was 3y? Well, that's what we're going to be working on soon here. So that brings us to our next series of steps. To add or subtract rational expressions whose denominators are different, find the least common denominator by finding the least common multiple of the denominators. So all that work we just did before this was getting us ready to find the LCM of the denominators. So it's going to involve factoring, just like we were doing, and picking out which factors we need for the common denominators. Step 2 says rewrite each of the original rational expressions as needed in an equivalent form that has the LCD. Step 3, add or subtract the numerators, write the result over the LCD, and then step 4, simplify if possible, meaning you might be able to reduce at the end, possibly. Okay, so I am going to switch us back to that whiteboard screen and do a quick review of just regular old how to add fractions with unlike denominators, because we have to be comfortable with that before we move on to these harder variable problems. So here's a quick recap, adding fractions review. I have 5 over 12 plus 7 over 30. Now, remember when we found the LCM of 12 and 30? We did all that work and we found that it was 60. I'm going to take us back a step and have us write the LCM as 2 times 2 times 3 times 5. I know that's ugly and maybe not as simplified as you would like, but that's really what our common denominators will tend to look like. It'll be a bunch of factors written next to each other. Okay, here's what I mean. So 5 over 12, I'm going to write this as 5 over 2 times 2 times 3. I'm factoring the 12. I know, we don't usually do it this way. And then for the 30, remember the factor tree we made? We got 2 times 3 times 5 for 30. Now, notice what the denominators already have in common. They already have a 2 in common and a 3 in common. What I like to do is ask, okay, what's missing from each fraction? So notice how this first fraction, the denominator is missing this factor of 5 in the denominator of the other one. We're going to multiply by 5 on the top and the bottom. Notice how the second fraction, it's missing that second factor of 2, right? So we'll multiply the top and the bottom by 2. Now, take a careful look at the denominators. They're now the same. 2 times 2 times 3 times 5. 2 times 2 times 3 times 5. That's the 60 that we would have gotten, but we're going to leave it factored right now. Okay, now let's put the numerators together, or at least simplify them a bit. So back to the first fraction, we're multiplying the top and the bottom by 5. I am going to multiply those numerators together, or this numerator by the 5. So 5 times 5 is 25. Okay, and then the other numerator plus 2 times 7, that's going to be 14. And we're putting that all together over one common denominator, the 2 times 2 times 3 times 5. Okay, now we're going to add the numerators together. 25 plus 14, that's 39. Still leaving that denominator factored. It would have been 39 over 60, and then you would want to reduce that. But I'm never writing it as 60. I'm just writing it factored the whole time. So now we're at the last step where we can reduce if possible. 39 can be factored into 3 times 13. Our denominator is 2 times 2 times 3 times 5. We can cancel out that common factor of 3. You would have done that if it was 39 over 60, except you might have written it like this: divide by 3, divide by 3, left with 13 over 20, right? We're going to do it in a slightly different way. We will leave the 13, but we're still going to leave that denominator factored. 2 times 2 times 5. Okay, we tend to leave the denominator in factored form. So I'm getting us ready for that right now, even though it looks unfinished, I know. All right, now we could build on this. Like, let's say instead of 5 over 12, it was 5x over 12. And instead of 7 over 30, it was 7y over 30. Then we might be done much earlier in the problem. Maybe we would have 25x plus 14y over the denominator, and then the problem would be over. So anyway, this could go in many different directions, but that was meant to just be a slightly, I know it didn't feel easy, but a slightly easier problem with just regular numbers. Let's go back to the notes and see how this applies to the problems with variables. Okay, so here's our example. 5 over 4x plus 6 over 2y. Okay, so it says the LCD is 4xy. Now, how do we know that? Well, let's go back and look at the denominators, 4x and 2y. Okay, the LCD, least common denominator, let's focus on the numbers first. The least common multiple of 2 and 4 would just be 4, because 2 already goes into 4. The x and the y, those are two different factors. We just need all of them to be put together in our new denominator. In other words, 4x, you could write that as 2 times x. 2y is just 2 times y. Put it all together, we need 2 times x times y, which is 4xy. Or maybe you take a totally different approach and you just look at each fraction separately and just ask, what's missing? What's missing from each fraction in the denominator? So for the 5 over 4x, it doesn't have that factor of y, so we're going to multiply by y over y for the first fraction. For the second fraction, it's missing this x from the first one, and we need another factor of 2 because 2 times 2 is going to become 4. Now, notice how we're getting this common denominator, 4xy, 4xy. The numerators, let's see, 5 times y is 5y plus, and then 6 times 2x is 12x. And we're done when we put those together, but we can't combine them because they're not actually like terms. So this problem is actually shorter than the one we just did a few minutes ago. So we have 5y plus 12x all over a common denominator of 4xy. All right. Let's do one more on our own. We're on the next page now. Okay. We're starting off with some problems that do have common denominators. So example 1, 9 plus 3x over x plus 2 over x. Okay, this is a good one to start with because we already have a common denominator. So there's really not that much work for us to do. Keep the common denominator of x and just add all the numerators. 9 plus 3x plus 2. So we have 9 plus 3x plus 2 all over a common denominator of x. And then we just simplify. What can we do in the numerator? Well, we can combine like terms. 9 plus 2 is 11. So we have 11 plus 3x all over x. And that's the final answer. All right. For the your turn problem, 5 plus 2a plus 4. Or I'm sorry, those are the numerators. I'm getting ahead of myself. It's 5 plus 2a over a plus 4 over a. The common denominator is a. We would add all the expressions in the numerator, and I would just do this in one step personally. So I would keep the 2a as it is, plus 5 plus 4 is 9. So I would write 2a plus 9 all over a. Or you could write 9 plus 2a all over a. And in case you're wondering about the a or about the x in the other problem, we can't cross those out because the only way we could simplify is if we had a common factor. So ask yourself, can I factor anything in the numerator? If you can't, then you're done. So we can't factor in either of these problems. So they're nice and short and they're done. Let's take a look at example 2. Okay, so 5 over 27x plus 8 over 9x squared. So what I'm looking at first is the 9 and the 27. So 9 goes into 27. So my common denominator, least common denominator, it's going to have 27. And then take a look at the variables. Notice how x appears in both denominators. Whichever one has the higher number of x's, that's going to be what we need for our common denominator. So in other words, we need the higher exponent. So the first denominator has just x. The second denominator has x squared. So we need the higher one, x squared. So we're going to aim to build up our fractions to have the least common denominator of 27x squared. Okay, so let's see how that works. 5 over 27x. How do we get that denominator to turn into 27x squared? Well, we already have the 27. What's missing? We need another factor of x. So notice how we're multiplying the top and the bottom by x. For the second fraction, 8 over 9x squared, notice the denominator. It already has the x squared, but this time what it doesn't have is the 27. How could we get the 27? Well, we would multiply the 9 times 3. That's our missing factor. Because 9x squared times 3 is going to give us that common denominator of 27x squared. Same thing with the first fraction, 27x times x also gives 27x squared. And notice how we're multiplying in the numerators. 5 times x is 5x, 8 times 3 is 24. Then we put them together. Again, with the numerators, they're not like terms, so we just kind of write them next to each other. 5x plus 24 over the common denominator of 27x squared. And that's our final answer. Let's take a look at the your turn. 2 over 15y plus 3 over 5y to the third. Okay, so let's see. We're going to start thinking about what our common denominator is and how to get there. So I'm looking at the numbers 5 and 15. 5 goes into 15. So if I could change the 5 into a 15, that will work. So my least common denominator will have a 15. And notice the variables of y and y to the third. We'll need the higher of those exponents, which is the y to the third. So our LCD, our least common denominator, is going to be 15y to the third. Now that we know that, let's start multiplying, and we'll kind of fill in what's missing from each of the denominators. So notice in this first fraction, it's 15y. How do we change it into 15y to the third? In other words, what's missing? Basically, we need 2 more factors of y. So we need to multiply by y squared on the top and the bottom. That's going to turn that first fraction into 2y squared over 15y to the third. Now for the second fraction, 3 over 5y to the third. We already have the y to the third. This time what's missing is we need a 15. So how do we change that 5 into a 15? Well, we would multiply the top and the bottom by 3, because 5 times 3 is 15. 5y to the third times 3 is 15y to the third. And then in the numerator, 3 times 3 is 9. Okay, and now for our final answer, we're just going to rewrite this as one single fraction. 2y squared plus 9 is our numerator, all over 15y to the third is our common denominator. All right. Example 4. So yes, it doesn't look like we skipped a number, and that was intentional, trying to hit the highlights and hit the important parts, maybe without totally overdoing it. So yes, it looks like I did skip over an example, and we're going to do example 4, not 3. Okay, this one is a subtraction problem. All right, so 5x over x minus 7y minus 4x minus 1 over 7y minus x. Okay, so here's what we should be noticing about the denominators. X minus 7y and 7y minus x. They're not the same, but they're almost the same. So if you may remember, if you ever notice a binomial with 2 terms with subtraction that sort of appears to be backwards, you can rewrite it by factoring out a -1. So in other words, if you see something that looks like b minus a, and you're really wanting it to be a minus b, but that's not the same, what you can do is you can factor out a -1, and then what you have left is a minus b, because when we factor out a -1, the signs of each of those variables changes. The b becomes a minus, and the minus a becomes a positive. So in this example, we're going to keep that first denominator as it is, x minus 7y. And then the second denominator, we're going to try to rearrange that one. Okay, now how's that going to work here? Let's see. Now I've been mentioning factoring out a negative, and it looks, as I'm looking carefully here, let's see, they're not factoring out a negative. I guess what they're doing instead is multiplying by -1. It has the exact same result. Okay, so either way is fine. Let's try to make sense of what's going on here so you can follow what the notes have here. Okay, so staring at this is not what I expected. Okay. All right. So again, the goal is we want a common denominator. Our common denominator is going to just be x minus 7y. That's what we're going for. So I was thinking of factoring out a -1 from the 7y minus x. You could just as easily multiply, as long as you're doing it to the top and the bottom. You could also multiply by -1. That works as well. So that's what's happening here. So -1 times 7y minus x, that's going to turn into minus 7y plus x, which is the same thing as x minus 7y. So that's what that's accomplishing right there. We're getting the common denominator. It's just that we also need to distribute that -1 into the numerator, and we would get -4x plus 1. It appears that they've now switched the order and written +1 minus 4x. So I guess what's happening here is we're multiplying the top and the bottom by -1, and that allows us to take these binomial expressions and kind of switch the order while switching the signs. That's what's going on. So the 4x minus 1 turns into 1 minus 4x. The 7y minus x turns into x minus 7y. Okay, now we still have more work to do. Let's see. So we have 5x over x minus 7y minus 1 minus 4x over x minus 7y. Now remember, when you subtract, you do need to subtract both terms or all the terms, however many there are. So it's a good idea to put that second expression in parentheses. And then what you'll want to do is distribute that minus sign. So we're writing 5x minus parentheses 1 minus 4x all over the common denominator of x minus 7y. And then let's simplify in the numerator a little bit. 5x minus 1, and then we'll have plus 4x. So we just get to put a plus sign in this next little box here. So 5x minus 1 plus 4x all over x minus 7y. Combining like terms, 5x plus 4x becomes 9x, and then we still have the minus 1. So our final answer is 9x minus 1 over x minus 7y. Okay, I found that one to be tricky. Feel free to pause and make sure you got that all down. I am going to erase my writing for this, and we'll do the your turn version, and I do want to scroll my page over to have a little more space so we can see another one similar to this. Okay, and I know I mentioned factoring out a -1, but I will try to model it after the example, which is multiplying the top and the bottom by -1, and that works equally well. And it fits with the whole theme of factoring, so I think it's good. All right, your turn, number 4. So 3m over m minus 5 minus 2m plus 1 over 5 minus m. So let's keep the first expression as it is, 3m over m minus 5. And then let's work on changing that second expression so that we'll have the new common denominator turn into m minus 5. Now, how can we change 5 minus m into m minus 5? One of those ways is to multiply by -1. So let's do that on the top and the bottom, just like we saw in the previous example. So I'm taking that second expression and multiplying the top and the bottom by -1. So that 5 minus m times -1 really would become -5 plus m, or in other words, it's going to be m minus 5, which is what we wanted. 2m plus 1, if we multiply that by -1, it's going to turn into -2m minus 1 if I distribute that. I know last time they switched the order. I wasn't a huge fan of that. I don't think there's a good reason to do that, so I'm just going to leave the order as it is. All right, so 3m over m minus 5 minus -2m minus 1 over m minus 5. Now we can start combining these fractions together now that they have the common denominator. And the common denominator is that m minus 5. So let's start rewriting the numerator. So we still have 3m. Now, when I distribute that minus sign, like it's a -1, it's really going to get all the way back to 2m plus 1. This is sort of weird. All right, so I distribute that minus sign. And we're back where we started, sort of. The -2m turns into plus 2m. The -1 turns into plus 1. Then we combine like terms. 3m plus 2m is 5m plus 1. And the whole thing is over m minus 5. All right, that was your turn, number 4. Tricky common denominators when they're those binomials that are being subtracted and a little bit backwards. So we're able to get the common denominator by multiplying by -1 sometimes. Okay, example 5. Oh my goodness, okay. It looks so intimidating, all right, but it's trying to be helpful with all the fill in the blanks. So here's example 5, 3x over x squared plus 4x minus 5 minus 2x over x squared plus 6x plus 5. All right, let's start by factoring. So we're going to factor each denominator. X squared plus 4x minus 5. That turns into x plus 5, x minus 1. And then the next denominator, x squared plus 6x plus 5, that turns into x plus 5, x plus 1. So our common denominator, thankfully we don't need all of those because both fractions already have that factor of x plus 5, and they only have 1 each. So we only need 1 of those in the LCD. So we do need x plus 5. We do need x minus 1, and then we also need the x plus 1. So that's going to be our LCD, x plus 5, x minus 1, x plus 1. So as we continue, we'll try to think about what's missing from each of these fractions, because they already have some of the factors that we need in the denominator, but some of them might be missing. So you can see it on your paper. I just scrolled past it, but remember, here's the LCD. There, I got it again. LCD right here. X plus 5, x minus 1, x plus 1. So let's think about what's missing from this first fraction in the denominator. It's x plus 5, x minus 1. What's missing is this factor of x plus 1. So we're going to multiply the top and the bottom by x plus 1 in parentheses. Meanwhile, in the second expression, that fraction already has x plus 5, x plus 1. So this time what's missing is this factor of x minus 1. And please put it in parentheses. I wish that that's how it was typed here. I just think it's a better idea. It'll remind you that you'll need to distribute. Okay, so I just put parentheses around the x minus 1s. All right, now we're going to carefully start simplifying the numerators, keeping our common denominators the whole way through. Sometimes when I write these, I literally just write LCD in the denominator, kind of as a shorthand, and then I rewrite it at the end. So let's start with the first numerator. 3x times x plus 1, we'll distribute the 3x. 3x times x is 3x squared, plus 3x times 1 is 3x. So we have 3x squared plus 3x. Meanwhile, in the second expression, let's distribute the 2x. 2x times x is 2x squared. 2x times minus 1 is minus 2x. Okay, so we have 3x squared plus 3x minus 2x squared minus 2x. Okay, now with this minus, we're going to need to eventually distribute that minus sign. But what we're doing next in this next step here is rewriting these two fractions together as one. So here's where we are. All right, so we're writing this all as one fraction, 3x squared plus 3x. That comes from the first, that first numerator. Minus parentheses, we'll fill that in with 2x squared minus 2x. Meanwhile, the common denominator is still there, x plus 5, x minus 1, x plus 1. Now we'll continue simplifying the numerator. We'll do that by distributing that minus sign. I'm just drawing some arrows here. So 3x squared plus 3x, and then minus 2x squared, and then negative times negative becomes plus 2x. Okay, pause if you need to. I'm going to scroll down to the next part, so make sure you got all of this down. Okay. Here we are. All right, I'll fill in just a little bit, I think. Okay, that was a 2x squared plus 2x. This was 2x squared minus 2x. All right. Okay, just checking. Okay, I think we're good. All right, so here's where we are. So 3x squared plus 3x minus 2x squared plus 2x. That's our numerator. Time to combine like terms. The x squareds combine. 3x squared minus 2x squared is 1x squared. And then 3x, positive 3x plus 2x is plus 5x. So we have x squared plus 5x in the numerator. This is often where we stop. But we're now at the last step of reduce if possible or simplify if possible. So what that means is factor the numerator if possible. And it is possible here. There's a common factor of x between x squared plus 5x. We can factor out an x. That's what's happening here. What's left in the parentheses would be x plus 5. So x parentheses x plus 5 is all over that common denominator, x plus 5, x minus 1, x plus 1. What's happening next is we're canceling out a common factor of x plus 5 in the numerator and denominator. And finally, we're done. So what's left in the numerator is x, and in the denominator is x minus 1, x plus 1. And thankfully, we never multiply those factors together in the denominator. We leave them in factored form. It's just easier that way. It's easier to cancel if possible. It's easier to see whether or not we're able to reduce or not. All right. Very good. So I'm going to briefly pause the video here. I do want to do the your turn version of this. I know this is a lot. We probably would have taken a break in class by now. So give yourself a break as needed and then come back when you're ready. Okay, so we're looking at a different screen now. I've just copied down the your turn problem, and it's a subtraction problem. Let's take a look. So this is your turn number 5. 2x over x squared plus 4x minus 5 minus x over x squared plus 7x plus 10. Okay, let's start by factoring the denominators. That's pretty much always where to start with these. If they're not the same, which they clearly are not, let's rewrite the denominators in factored form. And I guess we'll just rewrite the whole problem for now. So let's see, 2x over something minus x over something else. Okay, so let's start with the first denominator, x squared plus 4x minus 5. Setting up my parentheses, x. Factors of -5 that add up to 4, that's going to be plus 5 and minus 1. So x plus 5, x minus 1. That's for the first fraction. Now the second one, x squared plus 7x plus 10. Setting up parentheses, x times x. We need factors of 10 that add to 7. That's going to be 2 and 5. So x plus 2, x plus 5. Okay, so let's take a look at our denominators. Notice that they're not the same. They are not common yet. So we can approach this as what's missing from each denominator that the other fraction has. We can almost skip that step of what's the LCD because we'll get there anyway. Okay, so I'm not even going to write out what is the LCD because I think we're about to find out. So let's look at this first fraction, the 2x over x plus 5, x minus 1. What is missing from this denominator that the other denominator has? So in red, again, x plus 5, x minus 1. In blue, x plus 2, x plus 5. Notice what's in common. They already have that x plus 5 in common. So that's already there. That's not missing. It's all good. What is missing is this x plus 2. So we're going to start by multiplying that first fraction by x plus 2 over x plus 2. Now take a look at those three factors in the denominator. That's the LCD right there. X plus 5, x minus 1, x plus 2. We just kind of stumbled into it without officially finding it. That was it. And we're about to see it in the next fraction as well. X over x plus 2, x plus 5. What's missing from that fraction? Well, again, the x plus 5 is not missing. It's already accounted for. What is missing, in other words, what's missing from this fraction that is present in the first one is this x minus 1. So in the second fraction, we're about to multiply by x minus 1 on the top and the bottom. And once again, take a look at those three factors in the denominator, x plus 2, x plus 5, x minus 1. They're in a different order, but it's still the same three factors. Okay, so that's the LCD. Those three factors. Moving on, let's keep going. Okay, so what I will do next is start to simplify the numerators. Let's do that by distributing. 2x times x plus 2, that's going to become 2x squared plus 2x times 2 is 4x. All right, and then minus, so I'm just going to write over the LCD. This is what I meant before. It's a little shorthand. Minus, and then the second fraction will also be over the LCD. We got that part covered. Now we're working on the numerators. All right, next we're distributing this x. X times x is x squared. X times minus 1 is minus 1x. So here's our two fractions, 2x squared plus 4x over the LCD, and then minus x squared minus x over the LCD. Which means we can put those together, recognizing that we're about to subtract this second expression. Now, I might be skipping a step here. There's a little more rewriting in the notes than is maybe necessary. I'm just going to immediately go ahead and start distributing this minus sign into that second expression. So when I rewrite, I will rewrite that first numerator, both of those terms from the first numerator, 2x squared plus 4x. And now we're going to do the subtraction part. So we're going to write minus x squared. And then this negative times negative minus minus x becomes plus x. So our numerator is 2x squared plus 4x minus x squared plus x. Okay, we're getting closer to the end. At this next step, I will start actually writing the common denominator because we're going to need that very soon. I was just saving myself some writing in between. Okay, so again, the common denominator is these three factors up here in any particular order. I'll write it as x plus 5, x minus 1, x plus 2. Okay, meanwhile, in the numerator, we're combining like terms. 2x squared minus 1x squared is just 1x squared. 4x plus 1x is plus 5x. So we have x squared plus 5x all over x plus 5, x minus 1, x plus 2. So now we need to decide, are we done or can we simplify? Let's check to see if we can factor the numerator. And we can. X squared plus 5x has a common factor of x, so we can factor out a GCF. So x times x plus 5 is what we have in the numerator. Writing out the denominator one more time, x plus 5, x minus 1, x plus 2. Oops. Sorry. Little issues with the writing there. Okay, so again, x plus 5 in the numerator over x plus 5, x minus 1, x plus 2 in the denominator. So everything is factored. Now we can cancel out any common factors that we may have, and we do have one pair of common factors. It's the x plus 5s. We can cancel those out. And that leaves our final answer of x in the numerator over x minus 1, x plus 2. All right. And that is our final answer for the your turn problem number 5. Okay, I think that was the last official part of the notes. Let's go back and check. So I think after this is the practice exercises. Okay, so at any point, you can feel free to pause and go try the homework. If you're feeling good and you feel like you understand what's going on, that's great. I know it's hard to learn from a video. We will talk about some of this when we're physically in the classroom together soon. But for now, this is what we have to go off of. So for anybody who kind of needs a little more, I'm going to keep going and we'll do some of the practice exercises as well. So let's start with these true or false statements, 1, 2, 3, and 4. So number 1, to subtract fractions, they must have a common denominator. And by the way, the directions say classify each statement as true or false. So we're going to say true for this one. Because yes, to add or subtract fractions, we do need a common denominator. So yes, true. Okay, number 2, when adding rational expressions, we add numerators and add denominators and then simplify if possible. No. So we do add numerators only if there's a common denominator. Once we have the common denominator, we keep it. So I'm going to say we keep the common denominator. We don't add those. Keep the common denominator. But to answer the question, false. So when adding rational expressions, we do add numerators and we keep the common denominators and simplify if possible. All right, number 3 is about an LCM question. The LCM of 8x to the third and 4x is 32x to the fourth. No, that's what we get if we multiply them together, but so it is a common multiple, but it's not the least common multiple. So no, false. Now what is the least common multiple? Well, 4 goes into 8, so the least common multiple would just need an 8. We wouldn't need that 32. And then between those powers of x, we just need whichever one is higher between the 1 exponent or the 3 exponent. So just the 3 exponent. So the LCM would actually just be 8x to the third. Okay, and finally, the LCD of two rational expressions is the LCM of the denominators of the rational expressions. Yes, true. The least common denominator is the least common multiple of the denominators. All right, let's see what problems we have here. First, we have some practice finding LCMs by factoring. And then there's adding and subtracting rational expressions. And I'm going to scroll through and see if there's maybe one extra hard one we should do. Okay, I think I'm going to just have us do number 17 right now. Perform the indicated operations and simplify. All right, so this has 3 rational expressions together. 6 over m minus 2 minus m plus 3 over m squared plus m minus 6 plus 5 over m plus 3. So we need to know the common denominator. And I'll tell you, there's something a little bit predictable about a problem like this. It's not necessarily guaranteed, but it's very, very likely that this factor, m minus 2, times this other factor, m plus 3, is going to be equal to that middle trinomial right there. In other words, if I were to factor m squared plus m minus 6, let's just do that. Let's see, m times m, factors of 6 that add up to 1. It's going to be 3 and minus 2. Yeah, see, so when I factor the denominator of that second expression, it becomes m plus 3, m minus 2. That's the LCD right there. Because it's already a multiple of m minus 2, that's already there, and then it's already a multiple of m plus 3 as well. So that's going to be our least common denominator for this problem. Okay, so what does that mean? Well, for this first fraction, it already has the m minus 2, but what's missing is the m plus 3. So for the first fraction, we would need to multiply the top and the bottom by m plus 3. Okay, and we'll deal with simplifying that later. All right, now the middle fraction here, that middle expression, it's already good. We don't need to change it other than write it in factored form. So I'll just write minus m plus 3 over m plus 3, m minus 2. We already factored that denominator and it's all good. That is the LCD, so it's all set. No need to change it. And then plus 5 over m plus 3. What's missing from this one, it already has the m plus 3. What's missing is the m minus 2. So we'll multiply the top and the bottom by m minus 2. Okay, and now we very carefully start simplifying. Okay, so I think what I'm going to do is each one of these expressions will have something to distribute, and we'll try to write them all together in one fraction. The common denominator is still the m plus 3, m minus 2. Let's start with those first terms here. So 6 times m plus 3, distribute the 6. That becomes 6m plus 18. Then that middle term, minus m plus 3, we're going to distribute that minus sign like it's a -1. So we'll write minus m minus 3. And finally, distributing the 5, we'll write plus 5m and then minus 10. Okay, and now let's combine like terms in the numerator. 6m minus m, that would be 5m. 5m plus this other 5m is 10m. Then combining the numbers, 18 minus 3, that's 15. And then 15 minus 10 is positive 5. So I'm getting 10m plus 5. Is that right? Okay. Yep. Okay. All right. And then we still have that denominator of m plus 3, m minus 2. All right. And let's see if we can factor or simplify. We can factor the numerator. There's a common factor of 5. And we're left with 2m plus 1. So 5 times 2m plus 1. The denominator is still m plus 3, m minus 2. This happens sometimes. You can factor the numerator, but that doesn't really lead to anything. There's no common factors that we can cancel out. So we're done. We will leave the answer like this. You can go back and leave the numerator unfactored if it turns out there's nothing you can cancel out, or you can leave it factored. It should be fine either way. All right, so I will remind you the answers to the other practice exercises, as well as the notes and the your turns, all that stuff. You can find it in the learning and lecture materials for this module unit. And if you have other questions, please ask. I think we've gone on long enough, so I know we didn't do all of the practice exercises. We just did a couple of them. I encourage you to try some on your own, check your answers, and we'll be sure to do at least a few in class as well. Okay, I think that's it. So this is it for lesson 5.2. It was a difficult one for sure, so good job making it through. And go ahead and try the homework. Let me know what questions you have, and I'll talk to everybody soon. Thank you.